Okay, we have an interesting question here about this isomerization. So the half-life of the catalyzed isomerization of cis-2-butene gas to produce trans-2-butene gas was measured and under various conditions, and we've got some data. So cis meaning we've got these are on the same side, and then trans, these are on the opposite side. So this is a little bit more stable, which is why this is going to prefer the direction, the isomerization is going to go towards trans-2-butene. Now, talking about some kinetics here. The reaction is first order. Explain how the data in the table are consistent with a first order reaction. So what we need to understand is that for a first order reaction, the half-life is not going to depend on the concentration. The half-life is going to be the same regardless of concentration. And what we're seeing here is that for these three trials right here, they are the same. The half-life is the same regardless of concentration. So, or in this case, we're reporting it as pressure. But for the pressure of a gas, is this we're still talking about the same thing. This is essentially we're talking about concentration, right? If we have twice the pressure in the same volume, that means there's twice as many gas molecules in there. So that's in essence twice the concentration. So concentration and pressure here with a gas are essentially interchangeable. Now, so we're saying that the half-life does not change by pressure or concentration. So that would be Y. Now, calculate the rate constant K for the reaction at 350 Kelvin. And we want units in there. So what we're saying is that we know that when we're talking in terms of a half-life, we have this very handy equation that we can use. The rate constant is going to be 0.693 over the half-life. Right, so here we're talking about 0.693 over 100 seconds. Right, the half-life here is given in seconds, and we have 100 for each of these three trials. So that means just divide by 100, which means we just put two more zeros, two more decimal zeros right there. 0.693, and that's going to be inverse seconds, right? Seconds are on the denominator, so inverse seconds, remember, they want appropriate units, so if you don't have that in there, that's not going to be full credit. So 0.00693 inverse seconds. Now, a little bit of thinking. Is the initial rate of the reaction in trial 1 greater than, less than, or equal to the initial rate in trial 2? Justify your answer. So this is a little tricky because one might be tempted to think, oh, the half-lives are the same, therefore the rates must be the same. But that's not true, right? A half-life is a relative, it's something that's relative, right? It takes the same amount of time for something to go from 4 to 2 as it does to go from 2 to 1. Right, because the time for it to cut in half is the same, right? But going from 4 to 2 instead of 2 to 1, there's more reactions happening, right? The greater the concentration, the faster the rate is going to be because there are more particles that can collide. So the greater the number of particles, the greater the probability of a collision, and therefore the greater the probability of a reaction occurring, thus it goes faster. So the initial rate in trial 1 versus trial 2, so the volume is the same, temperature is the same, and again half-life is the same, but the pressure is half, which means there's half as many gas molecules in there. So it must start out, the initial rate will be less than for trial 2. Trial 2, there's twice as many particles, twice as likely that a collision will occur. So it'll initially be faster. Now, so we do have to understand that that's not the same. That doesn't change the fact that the half-life is the same in each case. It's just that the half-life, right, where that can apply from any concentration being cut in half. That doesn't mean the rates are going to be the same. The greater the concentration, the faster the rate. So that will be less than. Now, the half-life of the reaction in trial 4 is less than the half-life in trial 2. So we want to explain why. Now, what else do we notice that's different? Let's look at this temperature column here. Now, that is the key right there. Right? The temperature is greater. The temperature is higher. So what we're saying is because we have a higher temperature, now what does that mean? Well, for a higher temperature, that means that the average kinetic energy of the particles in the sample is greater, meaning they're moving faster, right? So kinetic energy is faster. They're moving faster. So what that means is that when particles collide, there's going to be a greater probability of a reaction occurring, right? There is an activation energy, and a collision must occur with greater than with enough kinetic energy, that with an amount of kinetic energy that is greater than the activation energy in order to get to that transition state and allow the reaction to occur. So if there is a greater average kinetic energy for the particles, it's a greater probability that a collision will have enough energy to surpass the activation energy. And if that means that a greater proportion of collisions will result in a reaction, which on the macroscopic level means it goes faster, right? So greater kinetic energy, more collisions result in a reaction, so overall faster, right? Greater average kinetic energy, greater probability that a collision will have enough energy to surpass the activation barrier. Therefore, more of the collisions will result in a reaction, and that means that overall the reaction goes faster. So that was an interesting one. We have this isomerization. We got some kinetic data. We talked about half-life. We talked about rate constant. We talked about initial rates, and we talked about dependence on temperature as it relates to activation energy.